Good morning to all. Let us discuss classification of relays based on function. The following relays are the important types of relays which are classified based on their function. These relays are induction type overcurrent relay, induction type reverse power relay, distance relays, differential relays, and translay scheme. Okay, all these relays are classified based on their function. So let us discuss about induction type non-directional overcurrent relay. So the induction type non-directional overcurrent relay operates when current in the circuit exceeds a preset value. Means in this relay, current setting will be provided. Okay. So when the fault current reaches that setting value or exceeds that current setting value, this relay will operate. Okay. So the current setting that is provided, you will call it as preset value. Okay. So the overcurrent relay construction is similar to that of our watt-hour meter type relay. So if you remember, in the watt-hour meter, there was an upper E-shaped electromagnet and a lower U-shaped electromagnet was there. Okay, similarly in this relay also we are having an upper E-shaped electromagnet and a lower U-shaped electromagnet. So this relay consists of two electromagnets. One is E-shaped electromagnet and an U-shaped electromagnet. In between this E-shaped electromagnet and U-shaped electromagnet, there is an aluminum disc, okay, which is free to rotate. Okay, in between these two magnets. Okay, so the spindle of this disc, this is the spindle of this disc, carries a moving contact. Okay, so it carries moving contact. This is the disc. Okay, this is the disc which is carrying moving contacts. Okay, and whenever this disc rotates, the spindle will rotate and hence the moving contacts will also rotate. Okay, so whenever these moving contacts are rotated, because of the rotation in the disc, these moving contacts will come in contact with the fixed contacts. These are the fixed contact, this is the moving contact. Okay, so these fixed contacts, these two fixed contacts, this and this contact, if you observe this contact, observe the cursor, movement of the cursor. Okay, here it has stopped, and this contact, if you see, this connection to this contact is given to this terminal. Okay, so these two fixed contacts are given to the trip circuit. Okay, they are given to the trip circuit. Okay, these two are the fixed contacts. You just observe the movement of this cursor and movement of this cursor. So they are given to the trip circuit. So whenever moving contact which is away from the fixed contacts, it comes in contact with the fixed contacts, what will happen is the trip circuit is closed. Okay, when the trip circuit is closed, trip coil is energized, and when the trip coil is energized, circuit breaker is open. So this upper electromagnet, which is in E shape, and the lower electromagnet, which is in U shape. Okay, so these two electromagnets are provided with some coils or windings. Okay, so if you see here, this is the upper electromagnet. It is provided with a primary winding and a single turn. If you see, single turn secondary winding. Okay, it is provided with primary winding and secondary winding. Upper electromagnet is provided with two windings. One is primary winding, other one is secondary winding. This primary winding is connected to the secondary of the CT on the line to be protected. So if we observe, okay, this is the primary winding which is connected to the CT. Okay, so I will show you another image. So this is it. So this is the primary winding. of the upper electromagnet, it is given to the secondary of the CT. This is one terminal. Other terminal is this, which is coming from this plug setting multiplier actually. Okay, so this the primary winding is connected to the secondary of the CT of the line to be protected. The primary winding is tapped at intervals. The tapping are connected to a plug setting bridge or plug setting multiplier. Okay, so this is our plug setting multiplier. So this primary winding is provided with tapping. Okay, so it is tapped at intervals, and this each tapping is given. If you observe my cursor, it is given to this. Next tapping is given to this. So this is how the primary winding tapped primary winding, each tapping is given to the plug setting multiplier. Okay, so approximately this whole primary winding is divided into 7 sections. Okay, so by using this plug setting multiplier bridge, we can adjust the number of turns of the primary winding, and hence desired current setting can be obtained. So the main reason for providing tapping to the primary winding is to get the desired current setting. Or in simple words, if you want me to say, to vary the time of operation of the relay, we are providing the tapping. So usually there are 7 sections of tapping to have the overcurrent range from 50% to 200% in steps of 25%. Okay, so in order to have overcurrent range of 50% to 200% in steps of 25%, the tapping is provided in usually in 7 sections. Okay, the adjustment of the current setting is made by inserting a pin. This is the pin you can see here. By inserting a pin between the spring-loaded jaw of the plug setting multiplier socket at the proper tap value required. Okay, so when this pin is withdrawn, when the overcurrent relay is in service, then the relay automatically adopts a higher current setting. Thus, secondary of the CT is not open circuited during service condition. So when the relay is operating, this pin should not be open. The secondary winding on the central limb of the upper electromagnet is connected in series to the winding of your lower electromagnet. Okay, if you observe, this is our secondary winding. This is the connection. Okay, so this is the secondary winding which is connected in series to the winding of your lower electromagnet. So whenever current flows through this primary winding, okay, so when current flows through the primary winding of your upper electromagnet, flux is induced. Okay, in the upper electromagnet, flux is induced. Okay, flux is induced in the upper electromagnet. Okay, let us assume the flux phi1 is induced in the upper electromagnet due to the current flow in the primary winding. Okay, so when this flux phi1 cuts the secondary winding, which is having a closed path here, EMF is induced in the secondary winding. Since it is forming a closed path, current will flow in the secondary winding. This current will even flow through these windings of which are wounded across the lower electromagnet limbs. Okay, and hence what will happen is flux of around phi 2 flux is induced. Phi 2 flux is induced in the lower electromagnet. Okay, flux phi 2 is induced in the lower electromagnet, and flux phi 1 is induced in the upper electromagnet. Both these fluxes will have fluxes as well as the current in the primary and current in the secondary will have space displacement as well as time displacement. Okay, so because of this space and time displacement between these two fluxes and the primary current and the secondary current, okay, this will result into a driving torque in the disk. Okay, a driving torque is induced in the disk. How it is induced, we have already discussed about while discussing about the working principle of induction relay. Okay, so driving torque is induced in the disk. When the driving torque is induced, actually initially under normal operating condition, there will be a spiral spring provided here in the spindle. The spiral spring will be holding this moving contact in position. Okay, this spiral spring in the spindle will be holding this moving contact in position, and this spiral spring will exert control torque. Okay, so because of that control torque, this moving contact is in position. Okay, so this spiral spring is providing a control torque. That's why this moving contact is kept away from the fixed contact. Now, because of the time and space displacement between the fluxes and the currents, okay, driving torque is induced. This driving torque will act in opposite direction to that of the direction of the control torque. Okay, and the moving contact, the disk will start to move, and this moving contact will come in contact with the fixed contact. So when this moving contact comes in contact with the fixed contact, automatically the trip circuit is closed and the circuit breaker is open. Okay, so for this relay to operate, and the current in the primary should exceed the preset value. Okay. So the angle of rotation of this disc will be in between 0 to 360 degrees, and the travel of the moving contacts can be adjusted by adjusting the angle of rotation of this disc. Okay, so this gives the non-directional induction overcurrent relay any desired time setting. Okay, which is indicated by a pointer on a time setting dial. So okay, so the travel of the means the desired time setting can be indicated by a pointer on a time setting dial. This dial is calibrated from 0 to 1. Okay, and this does not give the direct operating time, but it gives multiplier which can be used along with the time plug setting multiplier curve uh, to obtain the actual operating time of the relay. Okay, so with the help of this time multiplier dial setting, I'm sorry, with the help of this time setting dial and time plug multiplier, time plug multiplier setting. So this time plug multiplier setting graph or curve is provided by the manufacturer. Okay, so when the customer buys this relay from the manufacturer, along with the relay, he will also provide this plug setting multiplier curve. Okay, so if you know the time setting value, and if you know the plug setting, if you have the plug setting multiplier curve data, then you can easily determine the time of operation of the relay. If you are regularly attending my class, then you might have um, you might have learned already how to determine the operating time of the relay. So this time plug setting multiplier curve is provided, of course, it is provided by the manufacturer. Okay, the time required to rotate the disc depends on the torque. Okay, if the torque varies as the current in the primary circuit varies. Okay, so the torque, the amount of torque will depend on how much current is flowing in the primary coil here. So if the torque is more, the time taken for the disc to rotate will be less. Okay, means the time taken for the moving contact to come in contact with the fixed contact will be less. Okay, if the torque is less, the time taken for the moving contact to reach the fixed contact will be more. So hence we can say that this relay has inverse time characteristics. Okay, this relay has inverse time characteristics. This figure shows the time current characteristics of this non-directional overcurrent relay. Okay, so the characteristics which are shown here are called inverse definite minimum time characteristics. So these characteristics show the inverse relation between the time and the current for small values of current. Okay, so up to this margin, if you observe, the time and current are having an inverse characteristic. Means as the fault current is increasing, the time of operation of the relay is reducing. But after this margin, if you observe, as the current is increased further, okay, the time of operation is fixed. Okay, so it requires some definite time for the relay to operate. Okay, so a relay cannot be instantaneously operated. Okay, so means immediately as soon as fault occurs. Okay, of course there are instantaneous relays, but depending on the location and type of fault, okay, all the relays cannot be instantaneous. Okay, so this relay is not an instantaneous relay. Okay, so it requires some minimum time for okay, to operate. Okay, so if the current exceeds a certain value, okay, after this margin, if you observe, even though fault current is increasing, the time of operation is fixed, it is not varying. Okay, so the characteristics becomes almost a straight line at higher fault currents. Okay, so the IIDMT means inverse definite minimum time characteristics can be obtained by saturating the iron in the upper magnet. Okay, so you can saturate the this magnet, okay, ferromagnet, simply by allowing current to flow through the primary winding. What will happen is, as the current in the primary winding increases, automatically the flux phi1 will be increasing. So as the current increases, flux will on the upper electromagnet will also gradually increase, but at certain amount of fault current, okay, certain value of fault current, even though fault current is further increased, poles reach to their saturation level. When the poles reaches to their saturation level, they can't produce more flux. Okay, so when the poles are unable to produce more flux will remain constant. Okay. So this is the operation of your induction type non-directional overcurrent relay. Next is induction type directional power relay. We can even call this induction type directional power relay as induction type reverse power relay. Okay, we can even call it as induction type reverse power relay. So this type of relay operates when power in the circuit flows in a specific direction. Okay, so when the power in the circuit flows in a specific direction, then only this relay will operate. So induction type directional power relay, or we can even call it as induction type reverse power relay, it consists of an aluminum disc which is free to rotate in between this upper E-shaped electromagnet and lower U-shaped electromagnet. Okay, so upper E-shaped electromagnet central limb is wounded with a coil known as potential coil. Okay, and it is connected to a potential transformer. Okay, secondary of the potential transformer is given to this potential coil, and the lower U-shaped electromagnet is wounded with a coil known as current coil, and this current coil is connected to the secondary of the CT. Okay, so the current coil is actually provided with a number of tappings. You can see here in this image, the current coil is provided with number of tappings, and these tappings are given to the plug setting multiplier. Okay, they are given to the plug setting multiplier bridge. Okay, so the purpose of giving this the purpose of providing tapping to this current coil and giving it to the plug setting multiplier bridge is to get the desired current setting. Okay, so initially under normal operating condition, there will be a spiral spring in this spindle. That spring will be providing required control torque or restraining torque to keep the moving contact. This is the moving contact, these are the fixed contacts. To keep the moving contact in position means to keep the moving contact away from the fixed contact. Okay. Now, means for the moving contact to come in contact with the fixed contact, the disc has to rotate with some preset angle. Okay, so by adjusting this angle, the travel of the moving disc can be adjusted, hence any desired time setting can be obtained. So the flux that is produced in this upper electromagnet due to the current flow in this potential coil phi 1. Okay, this phi 1 will be lagging the applied voltage to this potential coil V by an angle of 90°, whereas the flux that is induced in this lower electromagnet will be almost in phase with the current in this coil of your lower electromagnet. So this can be seen in this. If you see here, if this is the voltage that is across the potential, across the secondary of your potential transformer, and if this is the current that is flowing into the current coil, then the flux induced in the upper electromagnet phi 1 will lag this voltage by an angle of 90°, and phi 2 that is induced in the lower electromagnet will be in phase with the current that is flowing in the current coil of your lower electromagnet. Okay, and of course these windings are inductive in nature. The current will be lagging the voltage by some angle theta, and phi 1 both the fluxes will have uh, phase I'm sorry, space and time displacement. Okay, so they will be having a phase displacement of alpha. Okay, so we already know the torque equation. Okay, we already know the torque equation. Torque is proportional to phi 1 phi 2 sine alpha. Okay, so where phi 1 is the flux induced in the upper electromagnet and phi 2 is the flux induced in the lower electromagnet, and alpha is the phase angle difference between these two fluxes. And phi 1 is proportional to what? Voltage V, and phi 2 is proportional to the current. Okay, and alpha is what? From this phasor diagram, alpha is 90 minus theta. Okay, so you can rewrite this torque equation as torque this as t is proportional to Vi sine 90 minus theta, where sine 90 minus theta is cos theta. Okay, so t is proportional to Vi cos theta. So Vi cos theta is nothing but power in the circuit. So torque is proportional to what? Power in the circuit. So it is clear that the direction of the operating torque or the driving torque on the disc will depend on the direction of the power flow in the circuit to which the relay is associated. Okay, so when the power in the circuit flows in the normal direction, okay, this operating torque and the restraining torque due to the spring help each other to keep this moving contact away from the fixed contact, and hence the relay will not operate. So whenever fault occurs, okay, so whenever fault occurs, whenever fault current exceeds the preset value, reversal of current will be there in the circuit which is to be protected, hence the power will also reverse in the circuit which is to be protected. So whenever reversal of power will occur, then this operating torque that is induced in the disc will also be in the reverse direction in this disc. That operating torque or the driving torque that is induced in this disc will also be in the reverse direction, and this magnitude of this torque will be very large when compared to the restraining torque or the control torque of the spindle, and hence this torque, due to this driving torque or operating torque, this moving contact will come in contact with the this moving contact will come in contact with this fixed contact. So when the moving contact comes in contact with the fixed contact, trip circuit is closed, trip coil is energized, and hence circuit breaker is open. When the circuit breaker is open, automatically the faulty section is disconnected from the healthy section. So these relays are usually used to provide reverse power protection to synchronous machines. Okay. So now to provide reverse power protection to the synchronous machines, these type of relays are used. Next type of relay is induction type directional overcurrent relay. So this induction type directional overcurrent relay consists of two segments or elements, that is overcurrent element and directional element. Okay, it consists of overcurrent element and directional element. So this overcurrent element will operate when current exceeds the preset value in a specified direction. Okay. So if you see one more image I am showing you. So this is the directional element in this circuit, and this is the overcurrent element. Okay, if you observe carefully here in this directional element, there is an upper electromagnet and a lower electromagnet, E-shaped upper electromagnet and U-shaped lower electromagnet. Similarly, in the overcurrent element also, there is an E-shaped upper electromagnet and U-shaped lower electromagnet. And both these directional element and overcurrent element both have their own discs. Okay, aluminum discs are there. Okay, and both have moving contacts. And if you observe in the directional element, there is a potential coil and a current coil. Okay, so potential coil is wounded across the central limb of your upper electromagnet, whereas current coil is wounded across the limbs of the lower electromagnet. And this potential coil is given to the secondary of the potential transformer. And this current coil, if you observe, this current coil is not only wounded across the lower electromagnet, but of the directional element, it is also connected to the primary winding of your overcurrent element, and it is given to the secondary of the CT. So the current coil is connected to the lower electromagnet of directional element and overcurrent element, primary winding of the overcurrent element, and given to the secondary of the CT. Okay, and the moving contacts of this overcurrent element, okay, so they are kept away from the fixed contacts of the trip circuit with the help of the control spiral spring, which provides the control torque. Okay, and if you observe, this is the secondary winding of the overcurrent element. This secondary winding from the upper electromagnet of this overcurrent element is connected to the lower electromagnet. Okay, it is wounded across the limbs of the lower electromagnet, and it is given to the, okay, it is given towards the it is entering into the directional element zone, where the secondary of this overcurrent element is kept open. So if you observe here carefully, the secondary of the overcurrent element is kept open. It is not short circuited, it is kept open. For the secondary winding of this overcurrent relay to close, okay, it have, or to short circuit or to close, for the secondary winding of this overcurrent element to close, this moving contact of your directional element should move towards this secondary winding terminals, and it should short circuit these two terminals 1 and 2. Okay, then only the secondary winding will be closed. Okay, so initially it is open. Under normal operating condition, the secondary winding of the overcurrent element is open. Okay, and for the overcurrent element to operate, for this overcurrent element to operate, the initially the directional element has to operate. If the directional element is not operating, then the moving contact of the directional element will not come in contact with these fixed contacts of the secondary windings of the overcurrent element. If the moving contact won't come in contact with this 1 and 2 terminals of this overcurrent element, then the secondary will not close. If the secondary will not close, then there will not be any fluxes that are means the flux will not be induced in this lower electromagnet of your overcurrent relay. Flux is not induced here in the lower electromagnet of your overcurrent relay. Then there will not be any time and space displacement between the fluxes of upper electromagnet and lower electromagnet, hence torque is not induced. Okay, so torque is not induced in the overcurrent element disk, okay, because the secondary is open. So whenever the directional unit operates, okay, or directional element operates, it closes the open contacts of the secondary winding of the relay, okay, and the overcurrent element will operate later. So under normal operating condition, power flows in the normal direction in the circuit protected by the relay, therefore directional unit does not operate. So when short circuit occurs, means whenever any fault occurs, there is tendency for the current or power to flow in the reverse direction. Okay, so in such case, the disk of the directional element, okay, the disk of this directional element will rotate, okay, because of the fluxes that are induced in both the electromagnets, and these two fluxes will have a space and time displacement. The resultant driving torque will cause this it will overcome the control torque, and it will cause the moving contact to move towards these fixed contacts. Okay, so when they come in contact with the fixed contacts, then the circuit of this overcurrent element will be completed, and the secondary are closed. Okay, so now when the secondary are closed, already fault current is not only in this lower electromagnet of directional element, already it is also flowing through the primary, because of the flux that is induced in the upper electromagnet. When this flux cuts the secondary windings, EMF is induced across the secondary windings, and since the circuit is closed here, current will flow through this secondary winding, and because of the current flow in these windings which are wounded across this lower electromagnet, flux phi 2 is induced here. So because of the interaction of the flux in the upper electromagnet of your overcurrent element and flux in the lower electromagnet, resultant torque or the driving torque that is induced in the disk will overcome, whose magnitude will be greater than the control torque, and it will cause this moving contact to move towards this fixed contacts of the trip circuit. When this moving contact comes in contact with the fixed contacts of the trip circuit is closed, hence trip coil is energized, and hence the circuit breaker is open. Okay, so the directional unit is made very sensitive. This directional unit is made very sensitive. And one more thing, this primary winding is provided, this see, the primary winding of overcurrent element is provided with the tapping to get the desired current setting. Okay, and this tapping are given to the flux setting multiplier bridge. Okay, so the overcurrent element, this is the overcurrent element. So the primary winding of the overcurrent element is provided with tapping to get the desired current setting value. So the directional unit is made very sensitive so that the lowest value of voltage, okay, which may be anticipated under severe fault conditions, sufficient torque is produced by the current to complete the operation and allow its contacts to close. Okay, means at lowest value of fault current, okay, the across the secondary, for lowest value of voltage, okay, this directional element will operate.